And buffer overruns, because it's so easy to make this mistake, you just need one spot in your code where you forgot to do bounds checking, and you have a buffer overrun flaw. And because there's so many ways to exploit it, in C and C++ code, buffer overruns are a security scourge. They're a real pain. They're endemic. So much so that I went and looked up this year's listing of the top CWEs. Each CWE is like a category of common weakness, like a type of vulnerability that you can have in your code. And they ranked them by like how common they are and how severe they are. And this year it happened to be the top one. Okay? And it's kind of been with us for decades, multiple decades, 2 decades, 3 decades, have been, top 1, top 5, somewhere in there. Okay, so this is one reason why we're teaching you about buffer overflows. Right. So partly because buffer overflows are such a problem, many modern languages are designed differently so that they won't be susceptible to buffer overflows. And the typical thing to see in a modern language is for the language to always bounds checks all memory accesses, all array accesses, all writes into buffers. Just have the language add that in by default for you so that you, the programmer, don't have to do that. So like Java does that for you, Python does that for you, a lot of modern languages, C#, as long as you're not writing unmanaged code, and so on and so on. So then, in those modern languages, we call them memory-safe languages, they don't have buffer overflow problems. So yeah, if you can use one of those memory-safe languages, you've taken an entire vulnerability class just out of the picture. You don't have to worry about it anymore. But we have a lot of existing code that was written in C and C++, both because it was written 10 or 20 years ago, because it's potentially better efficiency, because when you have code that was written, like Microsoft Word, first written, I don't know how long, 20 years ago, 30 years ago, and then it evolves, well, you got an existing code base, you tend to add to it rather than throw the whole thing away and start over again. So it's still a problem that's with us. Yeah. Why can't C? Well, there's a whole bunch of answers to that. One answer is C wasn't designed to do that. C was designed as like a slightly, just like a assembly language plus a little. And so your assembly language doesn't do that, so C doesn't do that. That's one answer. Another reason is in the early days, people were worried about performance. They said, well, developers will know when they're needed or not, so let's rely on the programmer. Another answer is in C, it's not so easy because like if I look at this code here, the argument passed to getS, there's no way to write getS that is safe with this API because it's passed a pointer to the start of the array, but it has no way of knowing how much space was allocated. So in Java, an array is actually an object that the language supports that has both like the start and a length. C doesn't have that concept. So it just kind of wasn't designed for this from the start, and so it's very hard to retrofit it. There are projects that try to retrofit this on, but it's painful to do. Yeah? Yeah, there's a lot of overlap here. Out of bounds write. You can see there's a out of bounds read. Those are kind of all instances of very similar problem. I don't know. I'm not going to worry about how they distinguish them. I would be fine with calling that a buffer overrun as well. And yeah, so they fall in the broader category of memory safety. Memory safety is kind of writing or a bug causes you to write or read somewhere you shouldn't be, out of bounds, basically.